All right, this is Mr. Gillum, and today we're going to learn some rules about some special right triangles. Okay, so there's right triangles obviously have one right angle, and the other two angles can be anything as long as they add up to the other 90 degrees. But today specifically, there's a couple examples of 30, 60, 90 and 45, 45, 90, and their special characteristics that I really want to talk about. It's going to be important for your trigonometry that's coming up. All right, so what we have here is a 45, 45, 90 degree triangle, and of course it follows all the rules of other right triangles as far as the Pythagorean theorem is applicable to it. So if I were to say, just make a little Pythagorean theorem statement, I could say that L squared plus L squared should equal the hypotenuse squared, or the leg squared plus the leg squared equals the hypotenuse squared. The reason I can call both of these L, I don't have to use like A, B, and C, is because this is an isosceles triangle, because they have two congruent base angles. So therefore its opposite sides are also congruent. So the nice thing about that is, if that is the case, it's specifically an isosceles right triangle with a 45, 45, 90. Instead of having three different variables, I have two variables. And so there's a relationship between the legs and the hypotenuse. If I simplify to 2L squared equals H squared, and I continue to solve, it looks like something L squared equals H squared over 2. Okay, this relationship is always 100% accurate in a 45, 45, 90 triangle. It's a pattern. Okay, if I get L completely by itself, what I have is L equals the square root of H squared over the square root of 2, or L equals H over the square root of 2. But of course, I'm going to want you to rationalize that, so I'm going to multiply the top and bottom by root 2 over root 2. L must equal H root 2 over 2. Okay, so there's a relationship here. Whatever H is, we can find L if we multiply it by root 2 over 2. Okay, or if you might prefer to think of it this way. L is always whatever H is divided by the square root of 2. Even though this isn't rationalized, this is actually the relationship that is the most important. It's going to be easiest to simplify. Okay, so L is always the hypotenuse. A leg of a 45, 45, 90 degree triangle is always the same as the hypotenuse's length divided by the square root of 2. Okay, so let's just make this a broad general statement. As you can see here, I've got a little diagram here that says if I have the length of a leg, let's just say this was 4, then I would know that the hypotenuse is automatically 4 root 2. If I had something like this instead of that, I could say, if I had maybe the hypotenuse's length as 5 root 2, I would know that this leg would be 5 root 2 divided by root 2, or just 5. Okay, there's a relationship here. So I want to sum this up for you real quick, make sure we're all clear on this. If you have a leg, given a leg, multiply by root 2 to find hypotenuse. Given a hypotenuse, divide by the square root of 2 to find the length of a leg. All right, so that's basically that's what we need to know about 45, 45, 90 degree triangles. There's a relationship between the legs and the hypotenuse. So let's take a few examples here. 45, 45, 90 degree triangles. And remember, the way to tell the difference between a leg and a hypotenuse is that the hypotenuse is across in a right triangle from the 90 degree angle, and all triangles in general across from the biggest angle of the triangle. But in a 90 degree triangle, obviously the 90 degrees is always the biggest side. So X is actually a hypotenuse in this case. This is X. There's a relationship between the leg and the hypotenuse. If I know that the leg is 6, I know that the hypotenuse is 6 times the square root of 2. So without doing any arithmetic, anything, no Pythagorean theorem, nothing like that, I know right away that 6 root 2 is the length of X. Okay? It's just that simple. If you have a leg's length, you can multiply it by root 2 to find the hypotenuse's length. that's specific to 45, 45, 90 degree triangles only. It's a special relationship because it's actually an isosceles triangle. Okay. Similarly, if I'm given a leg this time, there's my hypotenuse is straight across. If I'm given a leg, 9 root 2, and this is a 45, 45, 90 degree triangle, it isn't labeled in there, but it is a 45, 45, 90 degree triangle. I know that this leg, 9 root 2, times the square root of 2 is equal to my hypotenuse, which in this case is x again. So 9 times root 2 is really 9 times the square root of 4, or hopefully by now you know root 2 times root 2 is just 2, or 9 times 2 equals x. X must equal 18. So this length is 18. And we could use the Pythagorean theorem the same way, but when we start getting square roots being squared and all this other stuff, things get tricky, and as well as when we end up doing a unit circle, there's a lot of relationships in 45, 45 degree, 90 degree triangles that if you don't know the tricks and the shortcuts and the patterns, then it's going to take you a long time to understand where all the radians come from. So it's going to be very applicable to trigonometry when you get to algebra 2. Very, very important. Okay, so 45, 45, 90 degree triangles. That's a type of isosceles triangle that is also a right triangle. And the relationship between the legs and the hypotenuse, if you have a leg, you multiply by the root 2. If you have the hypotenuse, you go backwards and you divide by the square root of 2. Okay? As I was saying, this time, because this is the hypotenuse across from the 90 degree angle, I know that they're giving me the hypotenuse of 5 root 2. The relationship between the hypotenuse and the legs is, if I divide it by root 2, I'll be left with the length of one leg. So in this case, each leg is 5. All right, it's an isosceles triangle. It doesn't say 45 in there, so I'm going to write it in. We are assuming this is a 45, 45, 90 degree triangle. Okay. Again, we are assuming that this is 45, 45, 90. Well, we don't have to assume on this one. This is an isosceles triangle. If this leg is 45 across from 45, if this leg is x and this leg is x, and I know the hypotenuse, it's just a matter of using the relationship that I know to find the leg. If I had a leg, I'd multiply by root 2, but in this case I have a hypotenuse, so I'm going to divide by the square root of 2. Now, unfortunately, Mr. Gilm doesn't want you to leave this unrationalized fraction as it is, so I'm going to make you rationalize it by multiplying by the square root of 2 over the square root of 2. Whenever you see a square root in the denominator of a fraction, what this is called when I multiply it by 1, otherwise known as root 2 over root 2, is called rationalizing. Okay, when I take root 2 times 18, I have 18 root 2. On the bottom, root 2 times root 2 is 2 itself. And now it's just a matter of reducing. Numbers outside the root reduce with other numbers outside the root. Numbers inside the root reduce with numbers inside the root. In this case, each x value is equal to 9 root 2. If you're not convinced, you can always multiply it by root 2 to see if you get back to 18, which in this case you will. And in all cases you will. Alright, so there's the relationships between a 45, 45, 90 degree triangle between its legs and hypotenuse. Now let's take a look at the 30, 60, 90 degree triangle. There's also some special relationships here. However, there's different relationships because we don't have two legs that are exactly the same. But there is an important relationship here. And what I started with here was an equilateral triangle. As you can see, I have 2x, 2x, and 2x. And 60 degrees, 60 degrees, 60 degrees for this angle. So what I did was I actually took the altitude here. I bisected this angle and I made a 90 degree angle right there. And so I have a 30 degree here, 30 degree here. I still have my 60s. And now I actually have a right triangle. So again, what I want to do is I want to look at the relationships between the sides of this triangle. Okay, so I'm going to specifically highlight just one of the triangles here. That's the triangle I'm looking at. And what I notice is that opposite the 30 degree side is just x. Opposite the 90 degree side, or the hypotenuse, is 2x. The relationship between the hypotenuse and the side across from the 30 degree angle, the shortest leg, is the hypotenuse is twice, not 2, so 2 times as big as the shortest leg. All right, and that I can observe just right here. This is a guarantee. I mean, if it's 30 degrees right here, this is half of the hypotenuse. It's a no doubter. Like 2x, half of that would be x, 100% of the time. So the side across from the 30, opposite the 30-degree angle, is always half the length of the hypotenuse. Okay. The relationship that's hard to figure out is this relationship here, the longest leg. And so again, I want to know this relationship, so I'm going to do the Pythagorean theorem. And we're going to call this length A right here, this altitude. And we're going to say A squared, of course, which is one of the legs, plus B squared equals C squared. All right, so let's take a look, because I want to know what this relationship is between A and the other two sides. So I know A squared plus X squared equals 4X squared. Subtract X squared from both sides. I now have A squared equals 3X squared. And finally, I'm going to take the square root of both sides. A must equal plus or minus root 3x, but I'm not going to put minus. We're talking about distance. It's never going to be negative. So what I have here is the square root of 3 times x. Okay, the square root of x squared is x. So there's a relationship here as well. X represents the short leg side. If I have the short leg side, I can multiply it by the square root of 3 to find the longer leg's side. So root 3 times short leg equals long leg. All right, so there's a relationship there. These are both vice versa as well. Obviously, if I had the hypotenuse, I could divide it by 2 to get to the shortest leg. If I had the longest leg, I could divide it by the square root of 3 to get the shortest leg. Okay, so it's just a relationship in 30, 60, 90-degree triangles that you need to have down pat. Let's take a look here. Here's my diagram. If a side is represented by S, the short length, the shortest side, the hypotenuse is twice that, and the longer leg is root 3 times that. Okay. So this diagram is going to be the important one. I think the 45, 45, 90-degree triangle one, the isosceles triangle, those rules aren't as bad, hard to remember because there's only one root that you have to remember, root 2. And these, you got to remember it's root 3. And there's two relationships to remember. The short side times 2 is the hypotenuse. The short side times root 3 is the long leg. So if I want to find x and y, what I'm given here on this first problem, of course, the hard one, is the long leg. Okay, and the relationship between the long leg and the short leg is if I can take x, or the short leg, times the square root of 3, I know it's equal to the long leg. So if I solve for x here, I know x would equal 15 over root 3, but of course, Mr. Gillum, he wants you to rationalize this, so we're going to multiply by root 3 over root 3. X equals 15 root 3 over 3, and finally simplify. X equals 5 root 3. All right, so 5 root 3 is representing the short leg right here. Now I could continue and I try to figure out some sort of relationship between this long leg and the hypotenuse, but if I already know the short leg, I might as well just use that information. I know the short leg times the square root of 3 must equal the not times the square root of 3. The short leg times 2 should equal the hypotenuse. In this case, y is the hypotenuse. So 10 root 3 must equal y. And if you look at this relationship here, 5 root 3 times 2 is 10 root 3. 5 root 3 times root 3 equals 15. So I know that this 30, 60, 90-degree triangle follows all the rules that we just put in place. Let's take a look at this next one here. It says, once again, we do have a 30, 60, 90-degree triangle. So I know that there's a relationship between this short leg here, crossing the 30 degrees, and the hypotenuse, right there. In this case, once again, they give me the 60 degree, the longer leg. And I know there's a relationship between the short leg and the long leg, where if I take the square root of 3 times the short leg, it should equal the long leg. So I'm going to go ahead and figure out what the short leg is first. And I need to rationalize my fraction. 12 root 3 over 3. And finally, reducing is important. That is key. 4 root 3. Now that I know my short leg side, I can figure out what my hypotenuse is. The relationship between the short leg and the hypotenuse is twice as big, so I know y must equal 8 root 3, or twice 4 root 3. And we'll save the rest for tomorrow.